YouTube. Hello, everyone, and thank you for dialing in from different time zone and in the US, despite the fact that we have a long weekend approaching, and some people are taking the time off. We have a great seminar today that was actually put together by Jean-Francois, who couldn't be here today himself to introduce the speakers and chair the seminar. It is my pleasure, though, to introduce two distinguished speakers who are going to talk to us about various aspects of advancing numerical simulations in space plasma, very kind of wide range of topics from boundary effects to turbulence. And the first speaker will be Matteo Faganello. He got his master's and PhD physics in the University of Pisa in Italy. And since 2019, he has been associate professor in Aix-Marseille University. He's in charge of the fusion plasma specialization of a physics master in the same university since 2020. And he has a broad range of interests going from Kelvin-Helmholtz instability, reconnection, turbulence, kinetic instabilities in tokamak plasma, and other applications. And our second speaker for the day will be Renaud Ferrand. He studied physics and astrophysics in Cold Polytechnique and as the astrophysics university in Paris. He did 3-year PhD at LPP laboratory in École Polytechnique, and he studied there turbulence and solar wind and interstellar medium. He's been a postdoc in NERA in National Office of Aerospace Research and work on the development of microwave sources for electric thrusters. He's now has a permanent position at CEA, which is Atomic Energy Commission, and he's studying their ionization processes in the high-level atmosphere and interactions between radiation belts and solar wind. So as usual, we will go through the talks first, and then at the end, hopefully we'll have plenty of time for questions and discussion. In the meantime, of course, please, folks, use the chat features if you would like during the presentations. Thank you, and Matteo, take it away. It's all yours.
Okay, thank you very much. So I will share the screen, and thank you for inviting me. The screen allow should work. This is my presentation. Okay, so I hope that I well understood what to do in this kind of seminar. In some sense, I will be the lawyer for the fluid codes. Okay, and I will present the advantages and also the limits of a fluid approach. These are the outlines of my talks. This may be probably useful when the talks will be online. Okay, but the main question here is why we should use a fluid code. Okay, it could be a magnitude dynamic and LMHD to fluid or multi-fluid code. The first question usually it is because it is cheaper with respect to a kinetic one, cheaper from a numerical point of view. But this point actually is less and less critical with the development of supercomputer and very efficient numerical scheme. And the second answer usually is that fluid code, it is okay if the phenomena we are interested in, okay, can be described by a fluid approach. So it is quite tautological, and it is usually okay if we look at large scale and low frequency evolution. Okay, but this affirmation what must be taken with care, because we know that there are phenomena like magnetic reconnection, for example, that are intrinsically multi-scale. Okay, we also know that we can start with something that is large scale, okay, but that during the nonlinear evolution is able to generate smaller and smaller scales, okay. And it is also important to know that the usual shortcut is state that as soon as we are low frequency, low with respect to the ion cyclotron frequency, for example, we cannot have resonances between particle motion and modes. This is not so true, okay. And there is a second bad point for a fluid approach, that for sure some phenomena are fully kinetic. So resonant wave-particle interaction like Landau damping, cyclotron resonances are kinetic phenomena. Particle acceleration or particle streaming along field line during reconnection are kinetic phenomena. We can mitigate this negative point by the fact that we can include part of this kinetic behavior in a fluid model, for example, using a Landau fluid model, including the gyroviscosity in our fluid model. But finally, we know that the complete dynamic of this phenomena is fully kinetic. Okay. So why people do insist in using a fluid approach? And a good answer is that reduction is good for understanding. Okay, this is true for the geometry, but it is also true for the physical description. Okay, a fluid code can provide the first insight into the dynamics. Okay, and it is usually easier to analyze. It can help in identifying possible mechanisms that are at play in the system we are looking at. And for sure, they must be confirmed by a kinetic description, but can be done as a second step. Okay, another good point is that some phenomena, even if they are at small scale or if they are multi-scale, are caught by a fluid description. One example is magnetic reconnection. If we focus on the magnetic evolution only, so on the evolution of the topology of the magnetic field, and we are not so interested in particle acceleration or in the fine structures that we can find, for example, in the electron diffusion region, okay, a resistive all-MHD code can do the job. Okay, and last but not least, a fluid approach is far more handleable for managing boundary condition and non-trivial equilibrium. Okay, for example, having open boundary condition in a kinetic approach is not trivial at all, and we know that known velocities of equilibria for starting a simulation are only a few. So that's a point for a fluid approach and not for a kinetic approach. So let's take an example. Okay, and this is the Kelvinian instability that develops in particular during nova periods along the magnetospheric flanks. Okay, there we have a strong velocity shear due to the fact that the solar wind is flowing around the magnetosphere. We have the magnetic field that is advected by the solar wind that is more or less northward, okay, and so in the equatorial plane the magnetic tension is quite low, and we can develop the Kelvinian instability. And we also know that during these periods when the magnetic reconnection of the subsolar point and in the tail is not efficient, okay, we still observe a very efficient transport between the solar wind and the magnetosphere. For sure, this transport is not related to collisions or to wave-induced transport. And one of the main actors that can explain this transport is the Kelvinian instability. This is a very robust phenomenon in the sense that it is observed for more or less any kind of orientation of the interplanetary magnetic field, but we are focusing on northern periods, and it is a very good driver. It is like an engine for the transport. It is able to take the energy, the kinetic energy of the solar wind, to convert this energy in magnetic energy by distorting magnetic field line, and finally this energy is released by the magnetic reconnection. And when magnetic reconnection changes the topology of the magnetic field, we can boost the transport. Okay. And so let's focus to the region that is close to the equatorial plane. Okay. And in that case, we can consider the magnetopause like a one-dimensional equilibrium configuration as a starting point. Okay, in the sense that each quantity here, I write for the velocity, okay, the fluid velocity is a function of x only, where x is the direction perpendicular to the unperturbed magnetopause. So if we have a velocity shear, we have something like an hyperbolic tangent of x over a, where a is the width of our magnetopause. For sure, we have also the magnetic field. So here we have a cartoon where we have the magnetic field that is normal. Okay, we have an horizontal velocity field along y, that is the direction of the flow, that is sheared with respect to the x direction, that is the one that is perpendicular to the magnetopause. And we know that for the magnetospheric parameters, the Kelvin instability developed as what it called the fluid mode, in the sense that the wave vector is perpendicular to the magnetic field. Okay, and so if the wave vector is perpendicular to the magnetic field, and we can reduce the dynamics to a two-dimensional one in the plane that is defined by the inhomogeneous direction of the equilibrium, that is x, and the direction of the wave vector. On that plane, the configuration is an out-of-plane magnetic field, the guide field, okay, and the sheared velocity. For sure, the configuration is a little bit more complex, and we can have a rotation going from the magnetosphere to the solar wind, for example, because in the solar wind we have a flow-aligned component of the magnetic field. And in that case, the wave vector of the most unstable mode will be the one that is perpendicular to the magnetic field at the center of the shear, the magnetopause in some sense. Okay, so if we reduce the dynamics to a two-dimensional one, in the dynamical plane, what we get a guide field, we get a sheared velocity, and we also have an in-plane magnetic field that is sheared too, and that has a null line at the magnetopause. Okay, and if we look at that configuration, this is a perfect configuration for getting the classical two-dimensional reconnection plus a guide field. Okay, we have all the ingredients that are needed. Okay, the first one is an electric current that is associated to the magnetic rotation, and the second one is the resonant condition, that is k dot b equal to 0 somewhere, in particular where our null line is. Okay, and so we can reconnect. The peculiarity here is that this system, if the velocity gradient is more important than the magnetic gradient, here expressed using the FM velocity, it is not unstable with respect to reconnection to the classical TIIM mode, but is unstable with respect to the Kelvin-Helmholtz only. Okay, but that's not a problem, because the Kelvin-Helmholtz is able to pinch the original current sheet and to force reconnection to occur on that node line. And this kind of forced reconnection is called type 1 vortex-induced reconnection. And here we can see a picture of this dynamics taken by a very good article by Nakamura et al. Okay, and what you can see is a periodic chain of vortices. Actually, you can see only two half vortices. Okay, and in black you can see the field line that are advected by the fluid motion imposed by the growing Kelvin-Helmholtz instability. In particular, they are advected in opposite direction toward the null line, that is distorted too. Okay, and finally the connection is forced to occur, and here you can see the presence of what are called magnetic island, or if you prefer, magnetic field line that can connect the solar wind plasma to the magnetospheric plasma. The nice point from a model point of view is that this kind of evolution is well reproduced by both fluid and kinetic codes. For sure, if you are using a kinetic code, you can describe also the streaming of particles along the reconnected line, and so you can describe the transport of the plasma. Okay. We can also state that in this kind of phenomenon, type 1 vortex-induced reconnection, and the Kelvin-Helmholtz evolution there, 3D effects are quite weak, in the sense that the early evolution, also for the nonlinear phase, is more or less two-dimensional, also if you are using a three-dimensional code. And if you use a three-dimensional code, you can see that during the late nonlinear evolution, secondary reconnection events, secondary hydrodynamic instability develops a little more, and so the transport is finally enhanced by the overall picture of that phenomenon is more or less the same if you use a 2D or a 3D approach, if you use a fluid or a kinetic approach. Okay, and you have a problem if you want to use a kinetic approach, and it is the following. A common way for initializing a kinetic code is to adopt a shifted Maxwellian for the particle distribution function. Okay, so you have a Maxwellian with a fluid velocity here on y that is a function of x. The temperature is a function of x as well as the density, in order to reproduce the macroscopic profile that you have in the Magnetopause. And this PDF, this particle distribution function, it is not at all a Vlasov equilibrium. So the problem is that at the beginning of your simulation, you can observe a relaxation of your equilibrium that is not an equilibrium, so a relaxation of your profiles, and also you can observe persistent oscillation during the simulation. So these kind of simulation are not easy at all to perform and to analyze. But let's try to enlarge the view and take into consideration not only the low latitude region close to the equatorial plane, but also the high latitude region. Okay, and it is important because, okay, high latitude region are more or less stable with respect to the Kelvin-Helmholtz instability, and this is because the magnetic configuration is more complex there, so the magnetic tension is more important. Finally, the Kelvin-Helmholtz is stabilized. But the fact that you have stable and unstable region can influence the wall dynamics. Let's take something simple, okay? So instead of doing a global simulation, let's take a box along the flank, and let's take more or less northward field line inside the magnetosphere in blue and in the solar wind in red, okay? But let's add something to our equilibrium that is a Z dependence, okay, for our equilibrium, so that the region at low latitude is unstable and the regions at high latitudes in the northern and the southern hemisphere are stable. And in that case, what we can see is that we will get a full three-dimensional evolution from the beginning of the simulation, and it is quite expected because for sure the Kelvin-Helmholtz will depend on x, that is the normal direction, will depend on y, that is the direction of the wave vector, the perpendicular to the field lines, and will depend on z2 because the stability conditions are changing with respect to z. Okay, and this is a picture from a resistive all MHD simulation of mine, okay, and you can get an idea on the three-dimensional evolution. You can see that the low latitude region here, you can see the equatorial plane is unstable. You can see two well-developed Kelvin-Helmholtz vortices. Here in blue, it is the magnetospheric plasma, and in red, the solar wind plasma. On the contrary, high latitude regions in both hemispheres, in the northern and the southern hemisphere, are stable. Okay. And you can also see that even if you started with more or less straight field lines, because the motion is intrinsically three-dimensional, okay, field lines are strongly distorted in a three-dimensional way. In particular, they are arched in opposite direction. And here in blue, you can see the distorted magnetospheric field line, and in red, the distorted solar wind field lines. Okay, here you have an explanation why they are distorted in such a way. Never mind, you can get a look in the following, okay? But the important point is, because they are distorted, you can create far away from the place where the Kelvin-Helmholtz is developing an important magnetic rotation, so current sheets. And this is going on at mean latitudes. And you know that magnetic rotation or current sheet is a favorable condition for a connection to occur. And in fact, what you can observe in the simulation is that reconnection goes on in the northern hemisphere and in the southern hemisphere. And for example, it is able to change these blue lines that are connected to the blue magnetospheric plasma everywhere for each latitude at the beginning. Okay, now you can create what are called double reconnected line, for example, pale blue line that are drawn here, okay, that are connected to the blue plasma in the northern hemisphere at high latitude and in the southern hemisphere at high latitude. They are connected to the red plasma at the equatorial plane. Okay, so the flux tubes associated to this line are closed on the Earth, so they are topologically part of the magnetosphere, but they are partially populated by the solar wind particle. So because this code is a fluid code, you cannot describe the actual transport, but you can infer the transport from the topological evolution of the magnetic field, and in such a way you can explain the transfer. You find the mechanism for explaining it. This is not in competition with what I've shown before, because as soon as you add a magnetic rotation at the beginning of your simulation, okay, you can have at the same time vortex-induced reconnection and the reconnection with big latitude. Okay. So the problem now is great, but how can we initialize our simulation for getting such dynamics? Okay, so the starting point is a two-dimensional equilibrium. It is two-dimensional because it is depending on x, the direction perpendicular to the magnetopause, and z, the latitude. It does not depend on y, that is the direction of the flow, that for the equilibrium only is a translational symmetry direction. Okay. If we have a two-dimensional equilibrium, we know that we can write the magnetic field using a flux function that provides the x and z component of the magnetic field plus the component along the invariant direction, that is the y direction. Okay, and we know if you could, that all the other MHD quantities, if you consider an MHD equilibrium, so By, the velocity, the density, and the pressure, are a function of psi only. And this psi, our flux function, that is nothing more, nothing less than the vector potential component along the y direction, must satisfy a Grashof-Ranoff equation for having an equilibrium. This is nothing more, nothing less than the force balance equation in field-aligned coordinates. Okay. Okay, never mind about the equation. Let's take a solution, so an equilibrium that is like that, and never mind about the form. Let's look to this kind of solution that is suitable for our problem. And here you can see a plot of psi isosurface, so in some sense, magnetic field line in the XZ plane, okay, where y is the direction of the flow and d is perpendicular to that plane. So this whitish region is the magnetopause, this is the magnetosphere, this is the solar wind, and the equatorial plane is that line, okay. And what you can see that the magnetic field lines are more or less normal, but are shaped with an hourglass-like shape, okay. And because the velocity field, okay, that is perpendicular to that plane, is a function of psi, okay, what you get that if you take the classical function for getting the velocity shear, that is the hyperbolic tangent, that here is a function of psi, okay, you get the velocity profile here at the equatorial plane as this shape, okay, and it's quite steep because here field lines are closer. On the contrary, if you look to the velocity profile at high latitude planes in the northern or in the southern hemisphere, what you get is a smoother profile, okay, because here field lines are more sparse. And because you know that the gradient, the growth rate of the Kelvin-Helmholtz instability is proportional to the gradient of the velocity profile and not to the velocity jump, okay, what you obtain something where here the Kelvin-Helmholtz stability will develop quite quickly, and it is very slow to develop there and there. So finally, you obtain an effective high latitude stabilization, and you can get the nice picture I've shown you before. Okay. If you want, you can add a y component for the magnetic field, that is a function of psi2, okay, and so at the same time you can get the high latitude stabilization that is provided by the shaping of the field line and the magnetic rotation, and you pass from a normal magnetic field inside the magnetosphere to an oblique magnetic field in the solar wind, and so you can have at the same time in your simulation vortex-induced reconnection and mid-latitude. But let's look to our starting point, that is the equilibrium, and you can see that this equilibrium is far from being uniform close to the boundaries, in particular the X boundaries. Okay, so this is a problem in some sense because you must assure force balance for the equilibrium only for sure. Okay, there at the boundaries, and the forces will depend on both the x and z derivative of your magnetic field, because the current is the curl of B and so on. Okay, so assuming that is not trivial for a fluid code, but feasible, and it is even less trivial for a kinetic one, because for a kinetic one we have the same problem that you have in a kinetic code. You must manage the gradients of the macroscopic fields, but as I stated before, it is hard to find a 1D velocity of equilibrium. It is even harder to find two-dimensional one. Okay. One possibility for dealing with this 2D equilibrium, okay, is to use field-aligned coordinates. For example, psi, L, a parallel coordinate, and Y. Okay. You can do different things, either do a specific choice for this equilibrium, this is too specialized, or you can use general coordinates, a code that use general curvilinear coordinates, wonderful, but it's quite hard to develop. Okay, in both cases, you must manage a lot of differential geometry. And you have a last point to deal with, that are boundary conditions. Okay. In any case, for the perturbation that are large amplitude in a nonlinear simulation, you must impose the proper choice for the boundary condition if you want, I don't know, conducting rigid wall, or on the contrary, transparent boundary condition, relative one, and so on. Okay. One way to deal with all these points is to take advantage of the hyperbolicity of the MHD equation. Okay, that's worked very well if you are using an MHD code. The MHD equation can be rewritten in this way, that is the most general way, where phi is the list of the MHD variable, the density, the velocity, the operation of the magnetic field, and AX, AY, and AZ are matrices containing all these variables. Okay, and if we isolate the x derivative contribution to this equation, so we are putting this term and this term in C, and we are focusing on that term because we are focusing on x boundaries, we can note immediately that this matrix AX can be diagonalized. Okay, so for each eigenvector, the associated eigenvalue is nothing more, nothing less than the characteristic velocity of the MHD modes. So you get plus and minus the Alphen velocity, because you have the right-going and the left-going Alphen modes, plus and minus the slow magnetosonic velocity, the same for the fast magnetosonic velocity, and just the fluid velocity for the entropy mode. Okay, and for sure you also have the Doppler shift. Okay, and in such a way you can decompose this contribution along the characteristics. Okay. And the nice thing is that you can rewrite this term as a linear combination of things that are called L's, okay, that can be seen as the nonlinear amplitude of the modes. So to the right-going, the left-going Alphen modes, the same for the slow, for the fast, and for the entropy mode. Okay, for sure the gradients are still there, because they are just hidden inside the definition of each L. Let's do an example. Let's take the continuity equation. So the time derivative of rho, that usually is just equal to the minus the divergence of rho times V. Okay, you can see that these time derivatives can be just rewritten as a linear combination of the entropy mode, the slow mode, and the fast mode. For sure, the Alphen mode is not there because the Alphen mode is uncompressible. Okay, and the gradient are hidden in the definition of the L. For example, in the definition of L0, you can see the gradient of the density and the gradient of the temperature. Okay, so the big advantage of doing this decomposition is that now you know where the information
Matteo,
is.
sorry for rushing you, but we're getting a little bit short on time, so I need to make sure
Yes,
that.
I'm very sorry. I've quite.
No, please. Yes, just to let you know. Okay, great. Thank you.
Okay, thank you very much. So the main adjunct is not now we know the direction where a mode is traveling. Okay, so where the information is carried. Okay, toward the right or toward the left, depending on the sign of the eigenvalue. Okay, so in such a way you can build, for example, this is just an example, non-reflective boundary condition. Okay, let's take the right boundary. Okay, at each point of the right boundary, for each time, you check the sign of each eigenvalue. Okay, if the sign is positive, it means that this mode is something that is going from the box to the outside of the box. Okay, this is an information that is going from the box to the outside. So you know this is information. You can calculate your L just calculating the gradient with the internal point, for example, with the finite difference scheme. Okay. If on the contrary, the characteristic velocity is negative, this is something that is going from the outside to the box. Okay. You don't have this information. You must prescribe what is going on. And so what you prescribe the fact that you have gradient in your equilibrium. So you prescribe the fact that L must be equal to the L given by the equilibrium. And if you want a non-reflective boundary, so everything is exiting and nothing is entering, you add to that just 0. At the same price, you can add something different and get reflective boundaries or inject waves or inject solitons, because this procedure is completely nonlinear. Okay, so let's conclude. And so fluid code provide a valuable insight into mechanisms that play in space, even for collisionless plasma. You must know the limitation that you have in your model for sure, and take the result with care. But the big advantage of fluid code is their versatility for managing complex equilibria and boundary conditions. In particular, the characteristic decomposition works remarkably well in MHD code, and with just some tricks, you can use it also in all MHD code and to fluid codes. So thank you very much, and sorry for being late.
Thank you, Matteo. Very interesting talk and a lot of material to think about. Let's move to our next talk of the seminar, Renaud. Please take it away.
I'm sharing a screen. Okay. And that should do it. Okay. So, well, thank you, Matteo, for this very nice talk. So for the second one, I will be talking about part of my PhD work, so that I did at the Plasma Physics Laboratory with Ferrand and Sébastien. And that will be focused not so much on using fluid codes to simulate kinetic effects, but more on using tools, equations originating from fluid models to study inherently kinetic phenomena. And for this, I will be using the example of turbulence in astrophysical plasmas. So I won't be describing in details the difference between the fluid and kinetic formalism, because Matteo already did this very well. The main point to keep in mind is that, well, the two carry different physics, and normally a fluid description of a plasma should not be able to see kinetic mechanisms unless it was specifically constructed to do so. So in my work, I have mainly been focusing on the study of the turbulence inside the solar wind, and to a smaller extent to the near space it interacts with, so such as the Earth's magnetosphere. And this solar wind, being an average temperature and low density plasma, it can be described as a turbulent and collisionless plasma. So due to its proximity with Earth, of course, a lot of satellite missions were sent inside the wind to gather data, which helped to highlight the importance of fully understanding the turbulent nature of the wind to understand the underlying physics. One of the most common example is the one from the cooling of the solar wind that was found out in 1995 by Richardson et al. By studying data from the Voyager 2 probe, they showed that the cooling of the solar wind as it travels far away from the sun was much slower than what would describe an adiabatic model. And one of the most commonly physical effects used to explain this slow cooling is that turbulence inside the wind will bring energy to the small scales of the system, where it will fuel dissipation and heating mechanisms. So if we are to fully understand how energy is dissipated in the solar wind, we first need to understand how turbulence works. Which brings us to a fundamental question. What is turbulence? Well, basically, when you're looking at vortices, chaotic vortices made in water, in river, after water is crossing an emerging rock, for example, you're looking at a kind of turbulence. Here on the right, you have an example of a plasma simulation that was run with a pseudospectral code, in which you can see this kind of vortices, chaotic vortices, which are a marker of turbulence structure. So at the most basic order, you can describe turbulence as the chaotic creation of vortices in a low viscosity fluid in response to an external perturbation. The main problem with turbulence is that it's a very complex, nonlinear, and chaotic phenomenon. So there exist ways to study turbulence directly, but usually we will prefer looking at statistical tools in order to retrieve a certain sense of predictability. One of such tools, which is the one I have been using in my work, is the energy cascade rate. So let's take the simple case of hydrodynamics and do a bit of phenomenology. If we take a very low viscosity fluid in which we inject a perturbation, you will create big vortices that will not be able to dissipate the energy they contain because we are in the case of very low viscosity. So instead of dissipating the energy, this energy will be transferred to smaller vortices without loss. The smaller vortices will not be able to dissipate the energy either, so they will create even smaller vortices. And so you will go down in scale until you finally reach a scale that is small enough for dissipation to finally kick in. So due to this low viscosity, you will get an entire range of scales that we will call the inertial range, where the energy will be cascading from one scale to another without loss. And so if you define the energy cascade rate, that we will note epsilon, and which is the rate of energy transfer between one scale to the neighboring one, well, this energy cascade rate will be constant in the entire inertial range. So studying this epsilon will give us information on the scales spanned by the cascade. Everywhere it will be constant, and an estimate of the dissipated energy because the amplitude of the cascade rate will correspond to the energy available at small scales to be dissipated. So it's a very powerful tool to study turbulence. Usually turbulence is mostly studied in the Fourier space because it's more practical to do so. And you get a very clear power law when you look at the kinetic energy spectrum that is characteristic of the presence of turbulence. In my case, I have been working in the physical space by using equations that we call exact laws, equations that depend on the model we use to describe the system and that are based on fluid description of the plasma, hydrodynamics, MHD, this kind of thing. These equations, these exact laws, are called exact because they do not require making clear cuts in the equation to get a result, such as, for instance, when you work with asymptotic developments. You take the equation whole, and all you need to get results are a few minimal hypotheses of statistical homogeneity and stationarity. Because we will be working with averages, we need these averages to be invariant by translation in time and space. And of course, we will need the existence of an inertial range, the existence of turbulence for these equations to work. So how do we get to these equations and what do they look like? The main idea is that we will try to correlate 2 points in space by defining an increment vector that we will call L. This correlation will be obtained by looking at the dynamical equation for an energy correlation function. So in the case of hydrodynamics, the v square over 2, but with v taken at the 2 points separated by the increment vector. By using the equations describing the system, so in our case, the incompressible Navier-Stokes equation, we will be able to develop this dynamical equation. And by steering a bit and making a bit of calculation, we finally end up with this kind of law that will express the energy cascade rate as a function of third-order increments of the variables of the system. So in this case, we will have third-order increments of the velocity field aligned in the direction of the increment we chose. So this is the simplest case that was rediscovered in 1997 by Antonia et al. From the basic work of Kolmogorov that was done in 1941. This method that I just described is used more or less in the same fashion to obtain exact laws for all other complicated models up to compressible all MHD, for instance. Always the same idea, you correlate 2 points by using an energy correlation function. You use the equation to develop it, and you finally end up with an expression of epsilon as the further order increments of your variables. So if you take compressible all MHD, you will have an expression that will use the velocity field, the magnetic field, and the density field of your plasma. In my case, I've mainly been focusing on the all MHD, both in compressible and compressible models, because we want to describe the energy dissipation of turbulence. And to do so, because this dissipation is expected to occur mainly at small scales, we need to be able to describe the small scales of the system. And this goes through the use of the Hall effect. When you build your MHD model, you will need at some point to get an expression for the electric field. And this expression is usually obtained by using the generalized Ohm's law, that gives an expression of E as a sum of different terms that you may or may not keep depending on the precision you want to get in the end. So here you have in the bottom an example of a magnetic power spectrum representing turbulence, and that was built by using data taken from different satellite missions. You have at the large scale the energy containing scale, so the beginning of turbulence, and after this you have different power laws describing different parts of a turbulent cascade. If we want to describe the MHD intermediate scales, we will just need to keep the induction term. If we want to go below at the subion scales, we will need to keep the Hall term to be able to describe what is happening here. If we were to go even below, we will probably need to keep the electron-related terms. But of course, doing so comes with a drawback, because the more you increase the precision of your model, the more you increase the complexity of your exact law. And here you have an example of the compressible all MHD law. It's a nightmare to implement, and it induces a very high computational cost, especially when working with high-resolution simulations. Fortunately, and this is what I will be doing in this presentation, when you work with really lowly compressible datasets, you can get by using only the incompressible version of the law, which is much more simple to use. So here you have one of such incompressible all MHD exact law, where you have an expression of the energy cascade rate as a function of two terms, a blue MHD1 that will describe the intermediate scales, and the green all term that will describe the subion scales, and that is characterized here by the presence of di, the characteristic ion length. If we apply this exact law to a lowly compressible dataset that is part of the study that I will be presenting later, we will get this kind of plot that represents the amplitude, the arbitrary amplitude of the cascade rate and its component as a function of the scale that is expressed as the increment normalized by the ion characteristic length. So when you are here at 1, you are at the ion scale of your plasma. So if we plot the blue curve that is mostly merged with the red one, we see that we have something that is dominant at all the large and intermediate scales, and that will start to decrease at the near ion and subion scales. On the contrary, the all term in green is negligible at most scales and will start to become dominant at the subion scales. The sum of the two in red remains constant in almost all ranges considered. So here you get two good examples of a turbulence. First, we see the constant energy cascade rate that is characteristic of an inertial cascade. And we see the importance of considering the Hall term to fully describe our system. So this is this exact law that was derived for an isothermal that is similar to what we will obtain in a compressible isothermal closure. And this kind of representation, this kind of plot that I will be using in most of this presentation. So here it's an example on simulation data, but these exact laws have already been used extensively to study space plasma, starting with incompressible MHD laws that showed the inherently compressible what I'm saying. That shows, sorry, the inherently turbulent nature of the solar wind with here a clear linear scaling. What we plot in this plot here is the energy cascade rate times the increment. So instead of having something constant, you have a linear scaling, a power of 1. In more recent studies, more complicated models were used to compare the effect of the incompressible and compressible laws when dealing with compressible events. So you see that the red compressible model gives a slightly higher energy cascade rate than the black incompressible one. And in even more recent studies, we were able to show that when you work with even lowly compressible datasets, but at very low scale, so here very low sub-ion scales, you will need to take compressibility into account, so here with the red curve, to fully describe our system, because the incompressible model will not be enough to describe the small scales of your plasma. So a lot of different interesting results that were able to be obtained by using these fluid exact laws, with the hope, maybe, of using it to describe the dissipation in the solar wind and neighboring regions. And then we are reaching a small problem, because as I said in the beginning, our solar wind is a collisionless plasma. So being collisionless, you will not have viscous mechanism, you will not have viscous dissipation in the solar wind. So most of the energy dissipation is expected to happen through kinetic processes, such as wave-particle interactions, Landau damping, electron cyclotron resonance, this kind of thing. And the problem is that our exact laws stem from a fluid description of the plasma that has absolutely no idea that these kinetic mechanisms exist. So our cascade rate should not be able to see and transcribe kinetic mechanisms. So can we even use this tool to study solar wind dissipation? Well, a first answer will be yes, apparently it works, because it has already been done and it gives pretty good results. Here you have two examples of these results. First, on the top, with data coming from the Aix mission, where the cascade rate was calculated by using exact laws, and the heating rate was obtained by using a totally different method that gives an expression depending on the proton temperature by assuming an isotropic thermal distribution. It was shown that if you take the ratio between these two quantities, this ratio is close to unity for IMHD models of the exact law. So here typically in red and blue. Similarly, if you look at this study that was led on data from the MMS mission, and that you compute on one hand the cascade rate by using the exact laws, and the other hand the dissipation rate that was roughly estimated by using von Karman-Taylor phenomenology, you will get two pretty similar results despite using a fluid model and a totally decorrelated estimation of the dissipation. So it seems that our fluid energy cascade rate is still able to somehow transcribe this kinetic dissipation. So to better understand how this is possible, we decided to lead a more precise study focused on one single kinetic dissipation mechanism, which is Landau damping, by using an ensemble of data that was obtained by using the Landau fluid code. It's a code that was developed in Nice Côte d'Azur University, and that is able to produce two different kinds of data. First, it can produce CGL data, which is compressible all MHD data, but instead of using isothermal closure, we use an anisotropic pressure closure, which is the Chou, Goldberger, and Lowe closure. So this is basically a standard compressible all MHD simulation. On the other hand, we can produce Landau fluid data, which is more or less the same than the CGL one, except that we emulate the presence of Landau damping by slightly modifying the closure that is used. So here we have a way to toggle on and off our Landau damping at will. We are also able to modify the strength of this damping by modifying the forcing scheme of our simulation. So to force our turbulence, we inject waves at a given angle relative to the direction of the background magnetic field. And the smaller this angle, the stronger the damping will be. You can see this here by looking at the dashed line that represents the dissipative part of the dispersion relation of the Landau fluid model. And you can see that for the smaller 75 degrees angle, you have a lower curve relative to the 83 degrees one. So a stronger Landau damping. So with this code, we were able to produce a total of 8 datasets. 4 datasets, the CGL one that were forced without Landau damping, and 4 LF datasets that contain this Landau damping. And in each case, we have the run 1 and 2 that are forced with a weak and strong damping, and run 2, 3, and 4 that were forced at intermediate, small, and large scales, so that we can have a broad overview of our turbulence. And we will apply our previous incompressible or MHD exact law that has no idea that Landau damping even exists to this data and see what it gives us. So let us start by looking at the 83 degrees simulations, so the one with a potential weak Landau damping. If we apply our exact law and compare with the results, we see basically nothing. In this case, it will seem that Landau damping is too weak to really have an effect, and we see no difference between the cascade without Landau damping and with Landau damping. What we do see, however, is that the hyper dissipation that was artificially implemented in the code to drain the energy at the small scale of the system, and that is plotted here in purple, closely matches the red curve, the total cascade, at the small scale of the system, which means that the energy that is cascading is bound to be fully dissipated by this hyper dissipation. Now, if we increase the strength of Landau damping in the plot on the right, now we start to see things. First, we see that the cascade is reduced at all scales, suggesting that the Landau damping is acting at all scales of the system. But more interesting, we see that at the small scales of the system, the energy cascade rate is not constant anymore. So here we no longer have a perfect inertial cascade, and we are losing energy due to this Landau damping. And if we want to really highlight this effect, we can try to take the simulations that were forced at the 3 different scales and artificially reconnect the energy cascade rates to have a broad overview over 3 decades. And when we do so, we see that the CGL simulations in green give overall a constant energy cascade rate over the entire simulations domain. But the Landau fluid one only gives constant cascade rate at the large scales of a system, and it starts to decrease even more and even more as we go toward the smallest available scales. So here we have a very clear example that our fluid energy cascade rate can at least qualitatively feel the presence of kinetic Landau damping. What will be interesting now is to check if we can get a quantitative estimate, and to do so, we need to connect this energy cascade rate to Landau dissipation somehow. Without going into too much calculations, we can do this by looking at the energy balance equation of a cascading mode. So basically, the integral energy of a cascading mode will be equal to what is ejected minus what is dissipated by both Landau dissipation and hyper dissipation. Now, if instead of taking the integral form of this equation, we take the local one, we will get the energy cascade rate as a function of the integral between the large scale and an arbitrary intermediate scale K-pop of the injection minus the dissipation. And now if we take this arbitrary scale to be right in the middle, far away from the hyper dissipation and the injection, so basically somewhere around there, the hyper dissipation will be negligible and the injection will be taken whole, and so we'll get out of the integral, become independent of K. And now if we take 2 such scales and make the difference between the 2 cascade rates, the injection will vanish and we will get an expression of the variation of the cascade rate between 2 scales that will be equal to the integral between these 2 scales of the Landau dissipation. that we can obtain by looking at the heat fluxes and calculating by using the entropy, but it's a bit more complicated, so I will not go into further details. The important point is that we have a theoretical relation between the variation of the cascade rate and Landau dissipation. Now we need to check if this still holds when we compute epsilon by using our fluid exact law. So to do so, we take our small-scale, strong Landau dissipation simulation, so we can have the strongest Landau damping available, and we will take a reference scale, a fixed scale K-pub1. For every smallest scale K-pub2, we will compute this integral, and we will add the value back to the cascade as a corrective term. When we do this, we see that the corrected energy cascade rate is flattened as if we had no Landau damping. So the energy that was lost by the cascade is indeed equal to what was dissipated by Landau damping in between. So here we have a proof that we can get a quantitative estimate of kinetic dissipation by using only our fluid quantity. So in the end, in the case of turbulence that we study through this energy cascade rate, which is a fluid quantity, we are able to get several informations on the energy dissipated in our collisionless solar wind. First, the amplitude of the energy cascade rate will give us an information on the available energy to be dissipated now or a bit further in the cascade. And after this, we can look at the variations of the energy cascade rate. If it is constant, we have no energy dissipation. But if it is decreasing or probably increasing, we will have a loss of energy due to kinetic phenomena or potentially a gain of energy due to some instability that will inject energy in the turbulence. And this can be obtained even if we use our fluid quantity, and thus this injection or dissipation of energy is stemming from a kinetic phenomenon. And with this, I thank you for your attention.
Thank you very much. Unfortunately, we're a little bit over time, which sadly means that we last. No apologies are needed. I personally very much enjoyed both talks. They're very thorough, but what happened, sadly, it's not because people don't want to stay on, but they have other meetings and they drop off. So I hope that folks will reach out to you offline with comments and.
I didn't see that there were only the three of us in the end. Yeah.
Yeah, it's all right. So it's but because I mean, it's good thing is that these things are available on YouTube, right? So and anyone can watch it later. Thank you both very much, and have a great weekend. Thank you.
Well, thank you.
Thank you very much, Sasha, for organizing the seminar.
Yeah, that was very nice.